Now, after the spices, we are going to have a look at the general account of starch, and it will be in reference to potato. Now, firstly, what is starch? How can we define starch? Starch, as you know, it's primarily obtained from the plant tissues, particularly from cereals and potatoes. It's also called as amylum, and it's tasteless, odorless white substance. And the starch, it's made up of glucose units. The primary monomeric unit is glucose. So in order to understand the structure of starch, we have to first understand the structure of glucose. So let's have a look. Glucose, as you might be knowing, that it's 6 carbon compound carbohydrate with aldehyde group. Aldehyde group is C double bond OH group, and it's having polyhydroxy OH groups. OH is alcohol group and has a chemical formula of C6H12O6. See, here we are having these carbon atoms at these junctions, and these are 6, 1, 2, 3, 4, 5, and 6. And then we are having the aldehyde group, that is C double bond OH. CHO, it's an aldehyde, and then we are having many hydrox groups, as you can see these OH alcohol groups. So that's it is polyhydroxy aldehyde. It's glucose is polyhydroxy aldehyde. Another important thing about this glucose is not only about glucose, other sugars as well, they exist in D and L forms. So how can we designate L or D form to a sugar? We have to see that the carbon which is adjacent to the carbon atom having the terminal OH group. So here we can see terminal OH group is this, and it is attached to the carbon number 6. Adjacent to this carbon which is holding the terminal hydroxy group is carbon number 5 in case of glucose. So we have to look at the orientation around this carbon. We are having H in OH. Since in this we are having OH on the left side, to your left side we are having OH, so this glucose will be designated as L glucose, because here OH is on the this OH, it's on the left hand side. Now another form is D-glucose. This D-glucose, it has everything same, nothing had changed, everything else is same as the L-glucose, but just on the carbon number 5, which is adjacent to the carbon holding the terminal hydroxy group. OH and H have flipped. Okay, this OH which was on the left hand side, this has gone to the right hand side. So we are having this glucose as D-glucose. D and L isomers are the mirror images of each other. The spatial orientation of H and OH on the carbon atom that's adjacent to the terminal primary alcohol carbon determines whether the sugar is D or L. In case of glucose, it's carbon number 5, which we have already discussed. If the OH is on the right hand side, we say it's D glucose, and if it's on the left hand side, we say it's L glucose. Now, another important thing about this glucose is that it undergoes cyclization. So what we mean by cyclization, this structure is a linear structure of glucose. It's also called as Fischer projection. Now, if you will have a look, we are having 6 carbons, 1, 2, 3, 4, 5, and 6 carbons. Carbon number 6 is here. What happens? This carbon number 5 is having an oxygen which is electron rich. It's having these lone pairs and it's electron rich. It makes an attack on this carbon which is having delta positive charge, and because it is sharing its electrons with the oxygen by these double bonds, and as a matter of fact, what happens now, this C and O, they enter into a bond, and as a matter of fact, what happens, this oxygen, it takes all the electrons which were it takes the 2 electrons which it was sharing in this bond towards itself, expelling the hydrogen as a proton. Here this carbon, since it forms the bond with the oxygen and gets the electron from there, as a matter of fact, it breaks this double bond and pushes the sharing electron on this oxygen. So this oxygen now becomes electron rich and it forms a bond with the proton. So we are having C OC here. This H is removed as proton and will enter here. So here we are having COC, this double bond is no more. We are having COH here and H here. Fine. Now another thing is if we will slightly rotate the structure like this, we will get the structure as this. And another important thing is that whatever uh, is on the left side, whatever groups are on the left side, for example H here, they are on the left side of this, they will be facing in the cycle form, they will be facing towards the upper upper end, and whatever is on the hand side, it will be downwards in this representation. So now we are having the cyclization has taken place. We are having this C carbon number 5, carbon number 1 here. It has this double bond has removed. Now there's a single bond. We are having CO. This H has made a bond with the proton, so OH is here. And now this C, it has entered in a cyclization with this carbon number 5 via O. So C, O and carbon number 5 here. This carbon has CH2OH on the upper side and this H is on the lower side. Okay, and then we are having carbon number 2. Now this OH, it was on the right hand side, it will go towards downwards in this form, and this H, it was on the left hand side, it will go upwards. Carbon number 3, this OH, it was on left hand side, so it will remain on upper side, and likewise here. So this is the cyclic form of glucose, which we call as glucopyranose. Why pyranose? Because it's six-membered ring. We call it as pyranose. Why D? Because here we are having on the carbon number 5, we were having this on the left hand this OH on the right hand side. So on this carbon number 5, it was on the from the glucose it has formed. There we had this OH group on the right side, so it will be called as D-glucose. Now another important thing is that we have to look up on these CH2OH group and the OH group on the first carbon and CH2OH group on the carbon number 5. Since they are in same direction, okay, as you can see they are both in the upwards, we say it will be a beta anomer, it will be a beta D-glucopyranose. Had they been opposite, we would have seen we would have said that they are alpha. So we are having in ring form, we are having beta and alpha form. Beta is when CH2OH and this OH, they are on the same side. Now see, we are having now alpha D-glucopyranose. Let's have a look. Here, this CH2OH is on the upper side and this OH is on the lower side. Okay, upper side and lower side. So it will be called as alpha D-glucopyranose. Had they been on the same side, this OH, if it would have been on the upper side, we would have said it's a beta. But since they are on opposite side, one is on the upper side and another is on downside, we say it is alpha, and it's alpha D glycopyranose, which is the basic unit of starch. This is the animation showing the cyclization of the glucose. Now coming again to structure of starch, it's made up of numerous glucose subunits joined by alpha glycostic bonds. Now see, here the glucose units, they get joined to each other by the alpha glycostic bonds. Why alpha? Because here OH was on the downwards and CH2OH group was on the upper side, and this is glycostic bond formed between the two glucose units. We were having here OH on this group, and here we are having OH on this group. They form a bond together, and we say it is alpha glycostic bond. Now if you will see here, this is the carbon number first entering in the bond, and here of another sugar it is the carbon number 4. So more precisely we will say it is alpha 1,4 glycostic bond in the starch. Now starch has two components, one is amylose and another is amylopectin. Now, what's amylose? It's a water-soluble component of starch constituting about 15 to 20% of total starch content. Chemically, amylose is a long unbranched chain with 200 to 1000 D-glucose units held by alpha 1,4 glycostic linkage. Why alpha? Because CH2OH group on the carbon number 5 and OH on the carbon number first. They are on the opposite side. One is on the upper side, another is on the lower side, so it will be alpha. Why 1? Because the two glucose units entering into the bond, one participates by involving its carbon number 1 and another participates by involving its carbon number 4. So we are having 1,4 glycostic. See, starch is made up of two components. One is amylose, another is amylopectin. This time we are talking about amylose. Amylose is a long chain of these glucose units which are held by 1,4 glycostic bonds, and it's usually unbranched. There is no branch, we are just having a linear chain. Now another important thing about this amylose is that it can exist in disordered amorphous conformation or two different helical forms. It can the two amylose chains can twine together to form a helical form or a double helix, or it can bind with another hydrophobic gas molecules like iodine, fatty acids, or an aromatic compound. This is known as the V form of the amylose, and it's how this amylose that binds with amylopectin to form starch. This is the double helix, parallel double helix of linear chains of this amylose which have twined together. Via this amylose, we know it is long, unbranched, made up of glucose units which are held by alpha 1,4 glycostic bonds. Now coming to amylopectin. Amylopectin is another component of the starch, and its water insoluble polysaccharide is highly branched. Amylose was unbranched, but it's highly branched, and alpha glucose units, a polymer of alpha glucose units found in plants, it comprises about 80 to 85% of total starch. So this is the main component in the starch. Glucose units are linked firstly in the linear way like alpha 1,4 glycostic bond as we are having in amylose, but branching takes place at with alpha 1,6 bonds occurring every 24 to 30 glucose units. Let's understand it like this. We are having the glucose units as an amylose, and they are bound by alpha 1,4 glycostic bonds, but when 24 to 30 glucose units add like this, what happens after 24 to 30 glucose units, chain is formed at the carbon number 6 and the carbon number 1 of the another glucose units. A branch arises forming alpha 1,4 glycostic bonds. So amylopectin is a branched component of the starch which is having first a linear chain of these glucose units bound by alpha 1,4 glycostic bonds, then to every 24 to 30 glucose units have added, a branch arises wherein a carbon at the sixth position enters into bond formation with another glucose unit forming alpha 1,4 glycostic bond. Now we are having the starch. In this we are having amylose and an amylopectin. Amylose, as you know, it's of linear chain held by alpha 1,4 glycostic bonds. Then we are having amylopectin. There we are having the branch at the sixth carbon position. So we are having alpha 1,6 branch here. So these amylose and amylopectin, they twine together to form the starch. Now coming to potato starch. Potatoes are a good source of starch. The cells of the root tubers of the potato plant contain starch grains. To extract the starch, the potatoes are crushed. The starch grains are released from the destroyed cells. The starch is then washed out and dried to powder form. Now, starch derivatives are used in many recipes, for example, in noodles, wine gums, cocktail nuts, potato chips, hot dog sausage, bakery cream, instant soups, sauces, and in other cuisines. In pastry, for example, in sponge cakes, it's used to keep the cake moist and give soft texture. It's occasionally used in preparation of pre-packed grated cheese to reduce sweating and binding. The higher the starch content, the more the potato will break down when it's cooked. We will have the mealness in the potato. Potatoes that are high in starch are therefore absolutely perfect for baking and mashing or for making veggies or fries. Now, the morphology of these potato starch grains. When they are viewed under the microscope by adding some iodine drops, as you know, amylose component, it just binds with other components like iodine and gets stained. We get the starch grains like this, which are oval. Looking more at their morphology, we are having the potato starch grains like this. Here there's a core which we call as hilum, and then you can see the rings like these which are called striations uh, or layers. These are called as growth rings or layers. And then this starch grain, when the polarized light is passed through them, they give shape like this, dark and bright, forming a cross shape, which we call as extinction cross. Dark cross pattern seen as rotating when using polarizing light, as seen on the image on right. This is also known as Maltese cross. Now there are many varieties which yield a good amount of starch from the potatoes. One is Rio Grande Russet, which is a good variety of potatoes for obtaining starch. It's very flowery and gives you good amount of starch. And then we are having this waxy potato starch, which is extracted from the new potato varieties designed. Here we are having only the amylopectin. Remember, in this waxy potato starch, it's a new starch, genetically engineered starch, wherein we are having just amylopectin component, and here we don't have any amylose. It's extracted from new potato varieties. Now coming to some facts about potatoes. Largest producer of potatoes in the world is China. Largest producer of potatoes in India or country is Uttar Pradesh. And it was Irish famine or famine, or which was also called as Great Hunger, from 1845 to 1849, which was due to the loss of potato crop due to potato blight. This is all about the potatoes. Thank you.